welcome everybody on this Thursday, 19th of June. We are hosting this second webinar, which is today we will talk about propeller retrofitting. Some of you already joined us for our previous webinar where we were discussing the energy saving devices. So the energy saving devices is a hot topic nowadays, but the propellers, screw propellers have been there for centuries, and we have now the time to, this will be around 20-25 minutes talking about propeller retrofitting, but despite this very old technology, it's a very important one on a vessel because all the power we use goes through the propeller, generating the thrust. So despite energy saving devices can provide good advantage on the power gains, having the right propeller is even more important. So in this topic, this topic we will be discussing today in this webinar. In case it's time to retrofit your propeller, we will take a look on what are the main challenges and some practical aspects and what is the methodology for the optimization, so you can have a successful retrofitting with whoever you are carrying it out. So it doesn't matter you are buying a propeller for a small boat off the shelf, or you are making a huge 40-ton prop with a big player, you can still benefit of the knowledge we will disclose here, we try to make it very practical and not only focus on hydrodynamics. Okay, so let's move on and welcome everybody again. Okay, so why retrofitting? So the motivations and the triggers for a propeller retrofitting sometimes seems that it could be pretty obvious, but most of the time the biggest technical drivers, the most relevant are those. So we could be that our propeller was wrongly designed, that when it was built, maybe it's an old ship and the propeller, well, not even wrong, but maybe it was designed with the wrong tools or the wrong design points. Or it could be that our vessel faced operation change. Sometimes it's an operation change in terms of speeds in drafts and therefore power demand, or operation in the way the vessel is used. For sometimes offshore vessel is converted into seismic research, or a patrol boat is converted into a yacht. And this change in the philosophy of the vessel is moving us to make a study and improvement on the propulsion system because the needs are different. Some of the very frequent ones are also the damage or the need for having a spare one. So this is an opportunity to make a better design propeller or take that advantage to adapt it for a new life of your vessel, or that we need to apply an energy power limitation because of the exact regulations. So then if I will be using less power because of the regulations, it's probably a good idea just to make a propeller more optimized for this smaller power. And last but not least, when I am installing energy saving devices, sometimes those energy saving devices are increasing the load on the propeller slightly. And this is something that needs to be taken into account either by modifying the existing propeller or by making a new one and take advantage of this retrofitting of the ESDs to put the new designed propeller so the gain can be larger with both solutions working together, as we will discuss later. And the strategic opportunities, the most obvious is the fuel savings, which is how we will pay the bill. So this is how we calculate the return of investments, but also regulations that most of you already aware of. And the noise and vibration could be for solving noise and vibration issue, or to improve, for instance, if I change the role of my ship when I have a workboat that I will convert into a yacht, for instance, or pleasure boat, then what is accepted for a workboat is no longer valid for a passenger vessel or a cruise vessel, pleasure boat. So then the noise and vibration requirements change a lot, and this means that the propeller needs to be especially designed to handle that. Okay, and what are the most typical challenges? The most obvious are the mechanical and the space constraints. So we obviously always want the larger propeller, as large as possible, rotating at the right RPM. So that's not always possible. So we need to balance very carefully how is the new propeller the new propeller, the main particulars decided at the very beginning, because that will make a significant change, as we will see later. And then there is a big challenge, which is the available information, especially with very old vessels. Many of you probably have suffered from this, and we have seen many projects where it's very difficult and very challenging to get the right drawings. So the halves, shafts, and the seals, and even the steel drawings of the vessel, the hull data. So collecting all this data can be very painful, and very often we have to make a 3D scan or go for sister ships. So there are different ways you can go around this problem, but it's something that is very hot topic on the propulsion retrofit in the data. And the same for the operations, because how the vessel is operating in the past could be more or less guessed, but what will happen in the near future sometimes is unknown, because if the vessel will be chartered to a third party, maybe it's not clear with the operating speeds and drafts, and this can maybe the propeller cannot be optimized so much as it could be, because if we are making a decision, for instance, on cavitation margins, we need to know for instance, the aft draft or the operational power, and that's not so easy to guess for the future. And then for the final challenge, of course, is the money, because we have not a good engineering, and from the very beginning on the propeller retrofitting, we might see problems on the return of the investment, because the propeller is expensive piece of hardware, very often linked to a dedicated dry docking for exchanging, and the work for installing Bluefit logistics, and it's not something you buy every day, and it's very important to make it in the right with the risk and control. But for the return of the investment, it's always important to keep in mind that the strap of the propeller can be a significant amount of the money you can get back. The prices nowadays are for the scrap could be high. Let's say $3, $4, $5, $6 or euros per kilo, depending on the LME prices. Okay, then we like a lot this slide, which is the operational data, because it reflects very clearly what the importance of the operational data, and how it's a smart way of collecting it is to put the speeds, the drafts, and the trims, so we can identify the hot spots. The hot spots here could be like here, the red ones. This is the amount of time or energy I'm spending on each condition. So this helps me decide how is the design point, or how I choose several design points to balance my design on the real operational of the vessel. This is the past, so it's not so easy to have a table like this for the future operation. The same applies for the engine loads, which is somehow connected to this, RPMs and engine load, and the critical input for the design conditions. Okay, so when we talk, I have to make a sketch here. Let me take the pen. Okay. When we talk about the engine propeller matching, this will be the typical propeller curve with a small light running margin. This is my engine curve. We see here, and these are the engine RPMs. Being this 100% RPMs, and this is the brake power. As we see here, the red one is the propeller curve. So we define the operating point in regards to the EPL. No? So if you have an EPL, maybe your engine will be limited to this amount of power. So then I might be also limiting my engine to a different RPM setting. So in the end, my propeller will be moving. If I keep the same propeller, will be moving this or that direction, depending how loaded is my vessel, and how much is the weather conditions and other aspects. So when this is the overload area, you have to avoid that very often this remains unchanged. but it could well be that the turbocharger and the injection settings can be adapted, or the nozzles on the turbochargers or your engine supply can tell you this, so as to adapt this curve to the new conditions, and then that way you can make your new propeller curve with a new design that could be either here or move a bit to the left is something that needs to be considered very carefully. Also taking into account the specific fuel consumption. No? So as you know, the specific fuel consumption curves are something like this, which are like a fried egg. And this needs to be, the more information you know about the performance of the engine, the better decisions you can make. Okay, so when we analyze again the performance data of the vessel, we see here the RPM power. This is from a real vessel, a tanker. So we see the red one is the trial condition, and here is the chosen design point, and these are the ballast conditions. So here this type of diagram doesn't show the amount of energy spent. This is just the number of average per day. So this taken from the non-reports, but it's important because you are normally spending less energy on ballast. You're also doing less voyages on ballast than on full load, and therefore it's very important to analyze those diagrams, also to check to discard the points that are out of the average, and together with the diagram we have seen before, with the specific fuel consumption and any other item affecting this, like the wind-assisted propulsion, energy-saving devices, EPL. This is another way of checking where you will be with the new design. Okay, and when there is something that is very, very typically happening on smaller vessels, not on a large ship, you don't make this type of changes, but for those of you handling smaller ships or warboats, it's very frequent that the changing the propeller configuration. When we talk about propeller configuration, I refer to this. If you have an open propeller and you go for a ducted propeller, but you might be the other way around. And this way it's very important, the connection between the open ducted with the diameter, RPMs, and the clearance on the stern, so you can maximize the performance without affecting the rest of the machinery. So typically there is no change in engine gearbox, so you have to play with those cards and try to get the most out of it. In this case, with the ducted propeller, there is an issue with the type of nozzle. So we will make another webinar after summer talking about the ducted propeller design and the types of nozzles. And so the nozzles are no longer the standard 19A nozzles, but things are getting more complex nowadays, but it's a very interesting topic. Moreover, the monoblock propeller is the typical one with just casted in one piece, fixed pitch. Vaulted propeller is when you make a fixed pitch propeller with vaulted blades, which is becoming nowadays more frequent, and controllable pitch propeller, that obviously is the controllable pitch with vaulted blades. And then you can take advantage of this change to modify the lubrication system of the stern tube. So we are seeing cases where the stern tube is changed from oil to water lubrication, because the environmental pressure and avoid headaches with the seals. Some people is changing to a water lubricated stern tube. So this is affecting also the alignment on the stern tube, the fluid fill bearing on the shafting system, and this is an important topic because maybe the loads on your bearing and the length of the bearing and the clearances need to be checked with the maker. Okay, and the wake field and resistance. So the resistance at the wake field is the first calculation you will do. So And you will analyze the resistance with the sea margin correlated with the sea trials. And but here we just want to outline an interesting topic, that is the difference we have between the full scale and the model scale. So this is two calculations done in full scale and model scale, and you can see that the depth of this peak here in the model scale, which is shown here, is those ones, is way deeper. So the average Taylor wake is also different. When you integrate over the disk, the values differ somehow. So this is very important when you are studying a propeller in model scale. Even the extrapolation is available. Carrying out the CFD full scale analysis is very important to anticipate the performance. And this is even more important for the energy saving devices. So it's better always to go for going this way, much more accurate. You avoid the extrapolations and guessing. Okay, and then for the twin screw full scale, this is here in this case you can see here would be the shadow of the twin screw vessel, the shaft and the brackets. You can see how the speed is slowed down here. And what is important is the rotation of the flow, which goes in this direction typically. So you have to optimize the propeller with the real wake field, especially to optimize the efficiency in the twin screw vessels. Shouldn't be overlooked because there is a lot of rotation on the flow, which can benefit you. Okay, then before the optimization, you carry out the self-propulsion validation, which is the baseline where you will start from. So correlating with the sea trials, full vessel, full scale, rotating propeller, and carry out the base case, several speeds, sea trial condition, or maybe you have some laden conditions. The average figures from the new reports can be also checked. So you know that you are right, because you need a good baseline to optimize, so you know you are comparing with something as accurate as possible. Okay, and then this is a hot topic, the wind-assisted propulsion analysis. We are getting a lot of questions from customers about the wind-assisted propulsion. So leaving aside the aerodynamic issues, which is something that is obviously very important, or the most important for the performance of the sails, we will take a look on the aspects to be considered on the propeller operation. So for the wind-assisted propulsion, the most important one is that you have operation at partial load. No? So you imagine it's like if your vessel, instead of moving about the resistance curve, is going into a different resistance curve, which is much more light. No? So in this case, the propeller could be very, very low load, and this is affecting the performance, because I might be on a very kind of weird efficiency point. So I need to consider that. And the same into my engine curve, to know how my propeller with the different operation of the sails will move around. When the sails are not running, they are increasing the drag. When the sails are operating at the maximum, they are reducing the resistance. And all this, how my resistance curve is moving, is very important to take into account for the propeller. And then it's also interesting to mention the rudder interaction, because there is obviously side forces on the vessel and some leeway, and how is the rudder interactions affecting when I'm handling the sails and correcting the course, because this is also affecting the performance, and somehow these corrections are slightly affecting my propeller upstream. So with the wind-assisted propulsion, there are several interesting topics to consider. Okay, and then this is the most important one, how the optimization is carried out, but it's important as far as you have completed correctly the previous steps. So you need the right technical information, you need the right operational profile, you have to consider all what is around the propeller, the ESDs, the sails, or whatever you have, the rudder, and then for the final optimization is done with the iterative CFD-based designs with optimization process iterative, where you can carry dozens or hundreds of cases in the computation. In behind with rotating propeller. This means the propeller is rotating in the CFD model behind the ship, and there I'm carrying out the in-behind optimization. So I don't do the optimization in other conditions and then I run it, but I do it already with the rotating propeller behind the ship. And the targets, yeah, you need to achieve a certain thrust and with a minimum torque and keep the RPMs controlled, but also handling cavitation and the strength requirements. And the diameter and the blade number is very critical, especially it's a decision that is typically made at the very beginning. And then the parameters control is the typically outline, skew, area, pitch, thickness, camber, and sectional profiles. All this is modified, not in the same amount, but in the same order, but every designer has their own methodology. But in the end, you are always trying to make the propeller as light as possible and as efficient as possible with a control on the cavitation. Is where knowing the operational profile expected in the future is very critical in this step. Okay, and then with there are some synergies with the energy-saving devices. So as we explained in the previous webinar, the energy-saving devices affect the rotative relative efficiency of the propeller by modifying the wake field, among other aspects. But this rotation of the flow is I designed the new propeller for taking into account the geometry of the ESDs, either if it's a duct or if it's a fin or whatever I put in the front. But then this propeller might be also fitted with a propeller booster fin or a rubber valve, which is recovering some energy from the hub vortex. So the combined performance with the energy-saving devices is very important, because it could be that if I have an ESD, imagine you have a PVCF, but if you design a new propeller with a different load on the circulation on the hub area, it could be that my hub vortex is not so strong, and maybe the PVCF is no longer needed because I'm making the propeller more efficient already, and this small gain from the PVCF, which is typically very minor, is no longer there. So all these interactions are very important, and it's very critical to design the propeller taking into account all ESDs in full scale. Now, when you're doing model test, the boundary layer, the wake field has nothing to do with the reality, and all the extrapolations can make a mess in the figures and could be very dangerous on the expected gains. Okay. So the cavitation, the same. The cavitation is very important, and visualizing it, that checking the volume and how we see the dynamics of the bubbles, because not the cavitation can be erosive, so there are different ways of judging how bad the cavitation is. So it's something that needs to be careful check, so not to be too conservative on the design, because the cavitation costs money when you put a lot of area on load of propeller to prevent cavitation, but for a cargo vessel, yeah, you have to live with it. If you have some cavitation and it's under control, it's in the not very bad spots, it might be manageable. It's a trade-off between performance and durability, and yeah, but you have to avoid it when it's erosive, and also with noise and vibration. So this is when you depend a lot on the type of ship. Okay, just to finalize, talking about shafting, this here on the right, torsional vibration. So what is typically happening when you change your propeller, this is the stresses on the propeller shaft. Typically, these values here are moving, changing this frequency here, which is and this peak can be, if you reduce the inertia on the mass, is typically going down, and is moving depending. If you increase the mass, the frequency drops, and if you reduce the mass, the frequency goes up. So this will move to the right, typically with a lighter propeller. And then, very important, the slope of the shaft on the up bearing and the loads in the typically this intermediate bearing and on the engine bearings here, which is typically very far from the propeller, but is very delicate. No? So those bearings on the engine, but the most important is this one. So pay special attention to the slopes and the loads in the different conditions in your aft stern tube bearing. Yeah, and just to finalize the ice class and the water noise and Navy projects where these are the typical noise curves for, in this case from DMB, but are all very similar. So these are the noise levels and this is the frequency. So depending on what class notation you will have, you need to comply. You see quite different levels from 140 to 180 dBs. That's for those of you familiar with the decibels, that's a lot. And the ice class, a lot of finite element calculation need to be done and can affect also the shaft. So it's not only the propeller, the ice class, the shaft, and the rest of the dry landing is still connected. So whatever you do on the propeller, check the shaft because it's the pyramid stress philosophy is there. So we maybe have to make another webinar about that. Okay, so those I took those pictures provided by Mukesh Kenny from Vortexa Marine, which is has done a lot of retrofits himself. So he suffered a lot of these topics. So one day we will invite him to explain the biggest challenges he has faced in his life during all those projects. But the logistics can be a headache, and the planning is very critical because those are big. In case you are talking about a big propeller, but even a small propeller, the lead times nowadays can be large with the approvals, moving the prop around, blue fitting. And so take your time. Don't try to make this on a rush because it's a recipe for a disaster. So try to plan well ahead. Sometimes even 1 year ahead is the right time to start thinking on the retrofitting for a medium to large size propeller. Okay, so yeah, just to finalize, retrofitting is a balance between cost, performance, and compliance. So you need a lot of information to make it properly. The return of the investment can be good, but you have to make it in the right way. And if you do it in the right way, then you can avoid maybe exchanging other components that could be very expensive, like the shaft or the stern tube or the gearbox or even the engine. Okay, so with that's all. We leave now the floor open for the questions, and I think we have. I just would like to give a couple of minutes to Roberto Prever from Naos. I don't know if Roberto managed to connect because we have carried out a retrofitting with him recently with some CPP blades, and we thought was interesting to have him here for to listen to the let's say the experiences of ship design officers. So now she's a ship design office from Italy, and I don't know if Roberto is around because I cannot see him here.
Yes,
but
I'm here.
You are there. Okay, Roberto. So please let us know your experience as a ship designer and on the propulsion retrofitting. So because I think it's good to get your impressions or what are the challenges you see on this type of projects.
Yeah, it's too vast the argument, but anyway, retrofitting. We have recently this experience with VICUSdt that was very successful. That was the case of a quite old vessel where, by the way, the propeller was also quite damaged or weared. And the new propeller correctly designed has given a huge improvement. And if you imagine that the owner was operating the ship, I don't know how many years, but probably more than 5 to 10 years with a wrong functioning, you can imagine how much more fuel they have burned in those amount of years. And so how much, of course, that is important. I think they will have a payback period very short now, and even they can think to put the vessel on different routes because the increase of speed allows them to serve even a longer route in some other place. So that is very important. As far as it is important, the design of the hull in front of the propeller, because by correctly doing that, you can achieve a lot of better environment for the propeller to work, including a pre-rotation of the flow that we are used to do on our twin skeg vessel, which has demonstrated along the year to be quite advantageous. So yeah, propeller and hull design, they are the key for a good performances.
Right. Yeah, indeed. This when it comes to the wake field, is very, very important on the hull design on the new builds to take into account how the propeller will operate, and I know sometimes it's an effort to modify the stern, but in the long run, a good wake field and a good thrust deduction can make a huge difference between similar ships, and we have seen that in a lot of projects. So yeah. That's a good point.
Yeah.
Okay, Roberto. So thanks for your comments, and
thank you for your webinar.
I would like to, again, thanks everybody for joining. Also, if you have further questions, feel free to reach us. Later at any time. This webinar will be available for offline, so you can share or see again, or we are happy to support you, and thanks again for joining, and wish you a good day ahead. So thank you. Bye bye.